This is Mrs. Palmer-Quay with the fourth video for Module 11. In this video I want to talk about the colligative properties of freezing point and boiling point. A colligative property is a particular property of a solution that depends on the number of particles dissolved in the solution, not on what those particles are. Not all properties of solutions depend upon the number of particles. For example, electroconductivity, whether a solution will conduct electricity or not, does not depend on particles. It is not a colligative property. It depends on the identity. Ionic solutions will conduct electricity. Covalent solutions will not. So it is not colligative. But freezing points and boiling points are colligative properties. More concentrated solutions will have lower freezing points and higher boiling points than dilute solutions. So the number of particles does matter for freezing and boiling. Let's start with talking about freezing point. Freezing point is the temperature where a phase change occurs between liquid and solid. A liquid will turn into a solid at the freezing point. Incidentally, if you're coming the other way, going from solid to liquid, we call it a melting point, but it's actually the same temperature. Freezing point depression is the difference in the temperature between the freezing point of the pure solvent and the solution that you're working with. So looking at this chart over here, we've got our pure solvent, and as it is cooled, it cools down to a freezing point, and this our temperature is on the vertical axis here, so it freezes at this temperature, and then after it's frozen, since it's a pure solvent, it pretty much stays at the same temperature. In your solution, it will freeze, but it will freeze at a lower freezing point. And then because the freezing is determined by the number of particles, it actually continues to decrease in temperature as more of the substance freezes because it actually becomes more and more concentrated. The number of the thing that's actually freezing is the solvent, and so as you take that solvent out of solution, it becomes more concentrated and it continues to lower the freezing point even further. That's why the slope here continues to decrease instead of remaining horizontal. So just this little cartoon over here on the right, tries to show a way to remember that freezing point goes down when there are more particles in solution, kind of like, friends keep you from freezing because they're insulating you all around. And that's sort of what we think is going on. It's keeping the solvent particles from making the switch from solid to liquid because these other particles kind of get in the way. To calculate freezing points, you need to know a few things. You need to know the molality of the solution, you need to know the number of particles produced, and you need to know the freezing point constant for the solvent because there is a proportional relationship that is involved in freezing, and so we've got some freezing point constants. They will be given to you. You do not need to memorize them, but you do need to consider them in the calculation. So basically our formula is that our change in temperature will be negative of the number of particles, that's what the I stands for, times your freezing constant times the molality of the solution. So to just transfer that over here, it equals negative I kF and then M. We've got a question that asks, what is the freezing point of a solution of 400 grams of ethylene glycol? That's antifreeze, with the formula of C2H6O2 if it is in 500 grams of water. So let's start by figuring out molality. We'll take our 400 grams of ethylene glycol and divide it by its molar mass. So you can go and calculate this using the periodic table. You'll find that it's 62 grams per mole. So our the amount of moles that we have is 6.45 moles. In order to calculate molality, we need to divide that by the number of kilograms of solvent that we have, and so 500 grams of water is 0.5 kilograms. And then finishing up the math here, you'll find that is a 12.9 molal solution, so it does have quite a few particles in it. It should have a significant change in the freezing point. So then we plug things into our formula. We've got our change in temperature being equal to a negative times the number of particles, I representing how many particles we have. We really are only getting one, Ethylene glycol is a covalent compound. It's not going to fall apart into ions, so for every mole of ethylene glycol, you have 1 mole of particles. We multiply that by our freezing constant, and I didn't bring that over from the other page, but it's 1.86 degrees Celsius per molal. And so you will always be given this constant. You do not need to memorize it. And then we multiply that by the molality of the solution. And so once you go ahead and fill in all of the, or go ahead and do all the calculations, you'll find that the answer is a negative 24 degrees Celsius. That's how much the freezing point has changed. So what is the new freezing temperature? Well, we're talking about a solution of water, which normally freezes at 0 degrees. And so in this case, the answer is the same thing. It's negative 24 degrees Celsius instead of 0 degrees. The same is true for boiling points, just in the opposite direction. The boiling point is the temperature where the phase change occurs between the liquid and gas. And so instead of a depression, you have an elevation. The boiling point elevation is the difference in temperature between the normal boiling point of the pure solvent and the solution. Boiling points are dependent on pressure, on vapor pressure, which is determined by atmospheric pressure. So we need to look at the boiling point at a particular pressure. So at 1 atmospheric pressure, our solvent boils at this temperature. So temperature is on the horizontal axis on this chart. And our solution boils at this temperature, at a higher temperature. And a little illustration on the right shows how these other particles kind of get in the way from the solvent making the transition from liquid to gas, and so that's why they have to have more energy. They have to be at a higher temperature in order to push their way out and move the transition from liquid to gaseous state. The calculating of the boiling point, the formula looks very similar to the calculation of freezing point, but we don't have a negative here in front of our I for the number of ions. We have a boiling point constant, and for water it's 0.512 degrees Celsius per molal, and then of course the molality of solution. So you can just tell from this constant that adding a little bit of solute into pure water has a much greater effect on the freezing point than on the boiling point. It takes a really concentrated solution to change the boiling point, but not quite so much to change the freezing point. Again, to just work through a calculation, what is the boiling point of a solution of 82.2 grams of calcium chloride in 40 grams of water? Calcium chloride, remember Cl or CaCl2, because calcium is from the second column in the periodic table, so it has a positive 2 charge as an ion, and of course chlorine it goes for the chloride ion with negative 1. So we want to start by figuring out how many moles we have so we can figure out the molality of our solution. So we take our 82.2 grams and divide it by the molar mass for calcium chloride, which is 111 grams per mole. And so this tells us we've got 0.741 moles. In order to figure out molality, we have to divide by kilograms. Again, we've got 400 grams, so that's 0.4 kilograms. So when we do the calculations, we find that we have a 1.85 molal solution. So then we need to just plug it into the formula. So our change in temperature is going to equal a positive number of ions. Well, how many ions are we going to get here from our calcium chloride? When it falls apart, they will all separate, 1 calcium and 2 chloride ions. So we need to multiply by 3 because there'll be 3 moles of particles for every mole of calcium chloride. Then we need our boiling point constant, which for water again is 0.512 degrees Celsius per molal. And then our molality of solution, which we just figured out to be a 1.85. So you go ahead and do all of the calculations, and you'll find that this equals 2.84 degrees Celsius. So that's the change in temperature. What's our new boiling point? Well, the old boiling point of pure water is 100 degrees Celsius, and so our new boiling point would be 102.84, or 103 degrees Celsius to 3 significant figures. So you want to be sure when you're doing boiling points and freezing points that you provide not only the temperature change, but what the final boiling point or freezing point will be. And then I just wanted to mention that osmosis, a process you may be familiar with from previous studies in biology or general science, is also something that's driven by colligative properties. Water or any solvent moves in and out of across the semi-permeable membrane because of the concentration of solutes. And I just have an example here from biology where you have a comparison between isotonic, hypotonic, and hypertonic solutions. And you can see how the movement of water across this membrane is determined by the particles there. And so osmotic pressure is very important in many biological processes, and it is one of those colligative properties. So this finishes what I wanted to say about how the freezing points or boiling points of solutions compare to that of the pure solvent.